Welcome to a lesson with Dr. Powell. Let's take another look at the function that we discussed in the last video, where we calculated the derivative intuitively. But let's make this a little bit more rigorous. So the function was the area under the curve y equals sine x, but we would go from 0 to up to a point x and take that area. And that would be the output of the function a of x. Now, what we can do is, in analyzing the difference quotient, we take the change of area, which is like the top part of the difference quotient, in computing the derivative as we take a limit. This is just simply the area under the curve up to like x plus h minus the area at x if we're looking at as we go from x to x plus h. So the area is simply just the area of the sliver here. That's change of A. Now this change of A area is sandwiched between two rectangles where the area is easy to compute. So it's sandwiched between a smaller rectangle and a bigger rectangle. The smaller rectangle is formed with the height on one side of this interval. So right at x, so sine x. Now, as we go all the way up, on the other side, we have the rectangle that has a longer side, so sine of x plus h, and the change of a is bounded above by the area of that bigger rectangle. So this change of a is sandwiched between these values, the area of the smaller rectangle, so height times width, and the area of the larger rectangle, height times width. Now, in here, let's replace change of A with what it is here, so it looks as we've seen before, and then divide by h as well. So we just replace this with this, and then we divide by h, but we divide everything by h. Notice that we divide everything by h, the h's cancel on the sides, and we're just left with this quotient being in between sine x and sine of x plus h. Now, as we take a limit as h goes to 0, we have by sandwiching that a prime of x actually goes to sine x as well. It's sandwiched right here, and so which means that a prime of x is equal to sine x. Now, this limit here worked because sine x is continuous. So since sine x is continuous, that's why we get this right here, meaning that as h goes to 0, this really does go to sine x because we can pass the limit in and out. And in general, if we're finding the area under the curve of any continuous function, the same similar type of sandwiching can happen. So if we're taking the area under any curve that's continuous, we get that the derivative of such a thing is equal to the y value of the curve itself. Thanks for watching.